The views expressed on Skeptically Speaking are not necessarily the views of this station, its affiliates, sponsors, or advertisers.
Bring it on! The skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Schell gonna raise a little hell, metaphorically that is. Cause we're skeptically speaking.
Hello and welcome to Skeptically Speaking. I'm Desiree Schell and I'm here with Ethan Siegel. Ethan is a theoretical astrophysicist with a PhD in theoretical cosmology from the University of Florida. He's been a science writer since 2008 when he started the fantastic space science blog, Starts With a Bang. Welcome back to Skeptically Speaking, Ethan.
Thank you, Desiree. It's a pleasure to be back.
Now, you're here to talk about a new project involving science journalism, but before we get to that, maybe if I could just get your take on the big picture. So you have previously discussed in detail why it's so difficult to know if science reporting is reliable. Why is it so hard?
Anytime you get a major issue that's newsworthy, the reason it's newsworthy typically is because someone has the opportunity to profit off of it in some fashion. And this could be in a whole variety of ways. You know, you can have something that is of great interest for public health. You can have something that is of great interest as far as a scientific breakthrough, something that could apply to telecommunications or the energy industry or the pharmaceutical industry, but something that presumably is going to come along and have a huge impact on many people's lives. And when you get an issue like that, the people who are doing things the old way have a vested interest in keeping it going the old way because they are presumably making money doing what they're doing. People who have the new breakthrough want to push this new breakthrough, and that might be the issues of what you're hearing. In the meantime, there is this actual scientific truth behind all of this. There is this sort of, what does the science actually say? And the sole goal that science has is to say, like, hey, you know, when it comes to an issue like climate science, here's what we're doing to the atmosphere, and here's how the Earth is responding, and these are the things you should know. These are maybe the important things that should shape our policy. But that won't be the story that you hear. You're going to have to hear sort of this false balance. Same deal comes along when you have medical breakthroughs or issues. There's a lot of information out there about vaccinations or fluoride in your drinking water, and it's very difficult to separate who has interests where versus, well, what are the public health interests? And what I would love to see is a source that you could go to solely get what is the science behind this? What is the health behind this? What is the public policy that will shape public health behind this? And there are a great many people who will provide you with a portion of the story to highlight the position that they have staked out.
Well, what do you think is worse? Sources that are actively biased or more mainstream outlets that do fall into that trap of false balance, as you said?
That's a very unfair question, and one that gets posed to journalists all the time is sort of this idea of, I have to make this decision, right? Do I either come out and say, well, I may be biased, but, you know, I'm reporting these facts versus, you know, well, I'm not biased at all. I'm reporting all sides of this issue. I think that by framing that as the issue, you're blowing your chance at getting the point, which is, look, we found something that's scientifically interesting, and here's what it is, and I'm going to accurately represent it. I'm going to tell you the story of what this means. And I may have a stake in what I want this to come out as. I may say, look, you know, I hate the big tobacco industry and my dad died of lung cancer, and that may be my story. And I may be really opposed to the tobacco industry because of it. That doesn't give me license to go and distort facts about tobacco and nicotine and smoking and that whole industry. What that means is when there's a story that comes out, I'm going to accurately represent the story. I'm going to put it in its proper scientific context. I may frame it a certain way. Someone else may frame it a different way. But my primary goal should be not to misrepresent the story, not to mislead the news listeners into believing that an implausible position is plausible.
Now, what options do people currently have for finding the kind of accurate science and health news that you're talking about?
Well, from my point of view, you have to really go about it yourself. The onus is really on you. If you have news outlets that you trust, you may be surprised to learn that they are not as trustworthy as you think. And that goes from everything from the Wall Street Journal to the New York Times to the BBC to the Telegraph to news sources that have traditionally been regarded as sort of the paragon of what is a quality news source. These news sources aren't doing that. These news sources aren't fact-checking. These news sources aren't telling the whole story in an unbiased fashion. What they're doing is they are doing this false balance thing that you alluded to, where, oh, well, such and such said this thing, and we're reporting that. Well, you don't do that. You're not a stenographer. You are a journalist. It's not just your job to report what someone said. It's your job and go and dig up, is this thing that they said factually accurate? What are the facts behind it? And maybe when we unearth those should be the things we're reporting. What the facts actually are, not what someone said, regardless of who they are.
So this really puts maybe the less curious among us at a disadvantage, if you're saying you have to be responsible for going out and finding your own news.
In an ideal world, this news would be just brought to you, right? You would be able to just have a source where I'm just going to turn on and listen, or I'm going to Google away and see what comes up, and that's going to be the quality news that I'm searching for. In my experience, there are a few news outlets that come close to giving you maybe a multitude of opinions, but without sort of that counterfactual voice in there, without that misinformative voice. And in my experience, I can give you three. I can tell you ProPublica is pretty good. I think that The Conversation, which is an Australian outlet, is pretty good. I think they're the conversation.co.au. And I think Al Jazeera English is pretty good. But I'm not going to claim that any of these sources are unbiased. I'm just going to claim that if you read something there, the facts that they're reporting have likely been checked and are likely accurate. They're not misrepresenting what's out there. So those would be maybe some sources that I would go to for general news, but they're not going to cover everything. If you have some maybe medical news that you're particularly interested in, or you want to know something about the link between HIV and AIDS, or is fluoridation coming to your community, or has it been taken away from your community, and what are the public health ramifications of that? Those aren't really sources that are going to report on that. If that's the kind of news you're after, really the only option is to either just do some broad blanket search on the topic and hope that you are good enough at discerning what is accurate versus what is misleading from, to discern what is a good news source from what is not a good news source.
And the vast majority of people are not in that position to make that differentiation.
There are some very good sources out there, for instance, that have names that wouldn't lead you to believe that they are, and there are some very bad sources out there that have names that would lead you to believe these people know exactly what they're talking about. I don't have any issue naming names. If you want to look at something like, how should I vaccinate my child? How should I vaccinate myself? What should I do about the flu shot? There are groups out there called the National Vaccine Information Center, which is, I can tell from your reaction that you've heard of them. They are one of the most notorious anti-vaccine groups who still spread misinformation about how vaccines can cause autism and all sorts of other public health problems that they have been proven to not be linked to. There is a group called the Fluoride Action Network that spreads all sorts of discredited misinformation from 30, 40, 70 years ago about the dangers of fluoride in your drinking water. That's simply untrue, and yet they are cited all the time in many, many news sources. And so it's very difficult to be an expert on all of these topics. Most of us simply don't have the time to go out and learn for ourselves, what is the science behind these issues on this vast array of issues? We have other concerns in our lives and other uses of our time that we don't want to spend reinventing this wheel for ourselves. Presumably, that's what journalism should be. That should be the filter between, well, there's this cacophony of voices out there, but I don't want to hear what anyone says about anything. I don't want to know my dentist's opinion on cardiology. I want to know what cardiologists are saying.
And here's where your new project comes in. Tell us about it.
What I've been doing is, I've been involved science writing for a long time now, and I've gotten to sort of know the landscape about it. Who are the science writers out there who are knowledgeable and passionate about public health, getting science out there into the mainstream for everyone to sort of enjoy its benefits, to appreciate what we learn about it, and there are a great many sources that just do what I aspire to do, which is to provide you with the accurate information on the cutting-edge research that's being done, to put it into context, and to not misinform you or lead you awry in any sort of way. And what my new project is doing, it's called Trap It. I'm the head editor of the Science and Health featured sections over there. Trap It is this artificial intelligence engine that you can pretty much type in any topic you want, and it'll go out and collect a bunch of articles around the web. They've been vetted to make sure that they're not spam, but what the artificial intelligence software isn't good enough to do is to tell you, well, who's presenting misleading facts to you? Who is coming at this with some sort of agenda that leads them to misrepresent the news. And that's where I come in. As the head editor and curator of these sections, I go through this and I sort of train this software to better pull out what are the quality articles, what are the ones that I want to give to you, what are the ones that meet my standards for not having this misinformation, not having the counterfactual, misleading diatribes in there, what are the ones that are devoid of the demagoguery and the false information. And the ones that have those things that I don't want in there, those are unreliable sources for that issue. And it's very unfortunate that a large fraction of what you generally regard as quality mainstream news sources are simply no good for a variety of topics because they don't report accurate factual information anymore.
This is brilliant. Like your job is actually to train AI to recognize reliable sources.
It's incredibly challenging at the moment.
One would assume.
The AI that we use actually is something you may have heard of. Trap It. It grew out of the same project that Siri, Apple's iPhone product, grew out of. So they are our sister software, and we have the same technology driving our AI engine that they have driving theirs.
So how do you do this exactly?
The biggest thing that I do is for each individual topic, I go, just like any user of Trap It would do, is I go and I create a trap on whatever topic I want. And the software goes out and finds all the articles from news sources, organizations, educational institutions, blogs, magazines, anything it can find that is the most relevant to that topic, and that's what it returns to me. And then what I have to do manually is I go through this and say, okay, well, I'm going to take a look at all of these articles, and this is a good article that's reporting accurate information. It may be biased. I'm not at the point where I'm going to train bias out of it. But as long as what it's reporting is factual and not scientifically misleading, I don't care whether you're pro-fracking or anti-fracking. What I care about is, are you spreading misinformation about how the process of fracking does or does not cause earthquakes or does not contaminate your drinking water? If you are spreading misinformation about that, then I'm going to tell the software that we don't like this. Either we don't like this source because this source systematically misleads its readers on this topic, or we don't like this content because this type of content that shows up is misleading. Or I can go to the sources that get it right and tell it, hey, AI software, we do like this. Show us more things like that. And over time, I can build up a database of what are bad sources, and I can have the AI build up a database of what are the good terms that are going to pull in the quality articles and what are the bad terms that are going to keep out the bad articles, so that over time, what I wind up with is a collection of articles that continues to aggregate in real time based on whatever gets reported that should be vetted for scientific accuracy, that should be vetted for quality. In other words, it should be this big aggregator of news sources from around the world that come in real time that are devoid of this misinformation that we've been trying to weed out of our lives.
I love this a lot.
Thank you. Me too. I wouldn't be embarking on this project if I didn't believe in this. I think this is something that is necessary. I think this is something that would be incredibly useful for the world. And more importantly, I think this is something that does not yet exist. At this point, if you want news that is vetted for this type of accuracy, really your only option is to go around to a bunch of sources that you trust and collect their RSS feeds. And even then, you don't get it sorted topic by topic. You have to do all the legwork yourself. And I don't think that's right. I don't think people necessarily need to be spending their time doing that. There should be a service out there that provides it, and that's what I'm aiming to do.
But you are asking for our help.
This is a very large task, and I am doing my best as one person to stay on top of a whole variety of topics. But one thing I'm not is I'm not an expert in all of these fields. My specialty is physics, astronomy, a bit about high-energy physics, theoretical astrophysics. That's the background I come from. And while I consider myself well-educated and well-informed in areas like biology, public health, chemistry, computer science, a whole bunch of different sciences, I'm certainly not at the level of expertise that I am in my specialty. And so if there's anything that you see on these sites that you recognize, oh my, like, this has this article in it, which is from an unreliable source. This is counterfactual. This is misleading. This is not what is actually going on, or even worse, this is just someone's opinion who doesn't know what they're talking about. The software is not yet perfect, and my job is, it often changes over time as far as, we've discovered this new source, and now this new source is going to get into your trap, even though it doesn't belong. And so what I need is that feedback from users saying, hey, we want to help you keep this pristine. We believe in this mission, and you can help me to do my job better. You can help provide this service to the world. And all you have to do is send me an email when you find something that isn't good. Something like, hey, this
is crap.
This trap on heart disease. This has a lot of great information, right, but it also has information in there from, Marlboro, which is not accurate information about the link between smoking and heart disease. Or right, this has information in there from the American Beverage Association, if that's even what they're called, saying that this study that links Diet Coke to heart disease, if there is such a study, saying that this study can't possibly be right because how could a beverage possibly cause heart disease? Well, hang on. If there's a scientific study, I want the accurate reporting on the scientific study. I don't want the American Beverage Makers Association telling me what their opinion is on whether this could possibly be right or not. So if there's any information out there that is getting into these traps that shouldn't be, I want to know about it. At the same time, if there's information, quality articles, quality sources out there that we aren't discovering, let me know, because we want to be discovering those too. We don't want someone's voice to be silenced just because they're a little-known blogger out there, or they're new to the internet, or because our software has somehow just passed them over. We want every voice that's out there to come in and be a part of this conversation, to be a part of this news that you're receiving, as long as they're not deliberately trying to mislead readers through either omission of well-known facts or through a skewed presentation of what the facts actually are.
That was impassioned, sir. Ethan, thank you very much for being on the show, and congratulations on your new gig.
Oh, my pleasure, Desiree. And if anyone wants to check this out, the URL is trap.it. I run the featured sections of science and health news, and like I said, if you would like to help out with this, my email is trapit.science@gmail.com, and if you see something wrong, let me know.
And we definitely have included a link to Trap It on our site, as well as to Ethan Siegel's blog, Starts With a Bang, and that's at skepticallyspeaking.com. And we'll be right back with guest host Rachelle Saunders and mathematician Malcolm Roberts after this.
Skeptically Speaking wants you to question everything. To be a part of the discussion, call and record your question on our listener question line at Speak 73101. That's 773-257-3101. Long-distance charges may apply. Sunday nights at 6 Mountain Time, join our Ustream chat room to listen and ask questions as we record interviews live. Just click the Listen Online button at skepticallyspeaking.com. You can also email your questions and comments to live@skepticallyspeaking.com, or if you're on Twitter, tweet us at Skeptical Radio. To find out where Skeptically Speaking airs near you, to listen to past episodes, or download the weekly podcast, check out our website at skepticallyspeaking.com. While you're there, follow the links to connect with us on our Facebook page, our Twitter feed, or to subscribe to the show in iTunes. And now, back to the show.
I'm Rachelle Saunders, guest hosting today and keeping the host chair warm for Desiree for a couple of weeks. Today is the first part of our two-part special feature on a subject everyone either loves or hates. Yes, I'm talking about mathematics. Today we're talking applied mathematics and fluid dynamics with guest Malcolm Roberts. Malcolm received his PhD in mathematics from the University of Alberta in 2011 and has been working to understand the mathematical underpinnings of fluid systems and turbulence. Beginning in July, he'll be working on magnetohydrodynamic turbulence simulations at Marseille in southern France. Welcome to the show, Malcolm.
Thanks very much. It was a pleasure to be here.
So I think it's best to start with a quick overview of fluid dynamics first. What kinds of things and areas does fluid dynamics actually encompass?
Fluid dynamics happens around us quite a lot. Anything like air, which is a gas, so gases are fluids, or water or scotch, these are liquids. So those also are fluids. And you have more complicated things as well, like plasmas, where you have, like in the aurora borealis, where you have fluids, you have this gas, which is also interacting with magnetic fields. So, if you count solids, liquids, fluids, and plasmas as the four states of matter, then three of them are fluids.
So this fluid mechanics really encompasses things big and large, right from small things like the blood in your veins to big like solar events.
Yeah, it's really interesting. We can use like a few equations describe really a large variety of events on a really large variety of scales.
So now, before the start of the show, you were actually telling me a little bit about how fluid dynamics gets involved in making a good cappuccino, and I would love for you to share that with our audience.
Mathematicians can be described as devices which turn coffee into theorems. So, this is very important to mathematics. In terms of cappuccinos, though, the trick is in the foaming of the milk. The big thing these days is microfoam, which basically means that you want your bubbles to be really small so it's nice, like creamy on the tongue and like really tasty. So basically what you're looking for is small scales. So when you have bubbles on the top, that's really going to cause you a lot of problems. It's not going to be a good cappuccino. So when you steam it, you put the steaming rod just below the surface so you have this nice boundary layer effect, and that actually will advect or suck in air around it, which gets more air into the system. But it also creates some little bit of turbulence, which sends energy to small scales. These small scale bubbles are what you want, and also if you're careful about it, you can create this sort of big vortex happening, and this vortex will bring big bubbles to the surface. Then they get folded into the fluid in this sort of like subduction zone, and then it destroys the big bubbles, and then you just get like these nice tasty little small bubbles left.
So when I was researching this and looking at all the different areas that fluid dynamics has applications in, I was actually really surprised to see that there are also some applications in things like economics.
Economics, I mean, it's a very mathematical field. I've learned a lot of really interesting economics over the last few years. For example, the Navier-Stokes equations, which are sort of one of those fundamental equations of fluid mechanics. If you take away the advection term, then you get the heat equation. And this just describes how, if you have something hot in the middle and it's cold on the sides, then this heat will gradually move to the sides. Or if you have a drop of dye in a still fluid, this will gradually spread to the entire fluid. So, and this heat equation was actually used to describe economic events. And the result of this study, applying the heat equation to economics, actually resulted, I believe, in a Nobel Prize for the researcher.
So when we talk about the flow of money, sometimes we really are talking about the flow of money.
Yes, if only it diffused as well. That would be just awesome.
That would be lovely. I know I could use a little more of that flow. So what are the main ways that fluid mechanics differ from classical mechanics?
Well, fluid mechanics is classical mechanics, actually. When we deal with fluid mechanics, generally what we're talking about is things moving at low speeds on, moderate scales. So you're not dealing with quantum mechanics, so it's not quantum physics. And you're not dealing with really high speeds, so it's not relativity or anything like that. So when you deal with fluid mechanics, except in these extreme cases, you're dealing with classical mechanics, and it's actually been described as the greatest unsolved classical physics problem.
Fluid mechanics seems really complicated with all of the turbulence involved and that kind of thing. Does that make it more complicated mathematically?
Than quantum mechanics or relativistic physics? Well, not really, because there's really interesting stuff happening in all these areas, but there's still open problems left in quantum mechanics and in relativity and in fluid mechanics and classical mechanics. So, these are open problems. They're hard enough that nobody's really solved them yet. So there's still a lot going on, and I wouldn't really describe any one field as particularly more difficult than any other, because all of these people, in all of these areas of research, not just physics, but biology and chemistry and economics and all these things, they're all working on difficult problems which we haven't solved yet. So they have their own easy parts of it and your own difficult parts of it. But it's not like one is particularly easier than the other, I think.
Now, my understanding is that there's quite a lot of calculus in fluid mechanics. Is that correct?
Yeah, you got to bone up on your differential equations and stuff.
And for those of us who struggled in math or never took calculus, and I am raising my hand here, can you quickly explain what a differential equation is and what it tells us?
Well, a differential equation is actually a pretty simple thing. It's basically talking about how rates of things are related to each other, right? So if you're skiing or something like that, then the rate of change of your velocity, like how fast you're accelerating, depends on the rate of change of the height of the hill over space, or how steep it is.
Right.
So differential equations are really useful for describing a lot of physical things in the real world.
And it tells us a lot about the rate of change as well, I think, right?
Yeah, so it's rates of change and how rates of change of things interact with each other.
So now some of the fluids that you model actually have some interesting properties that you have to take into account mathematically, right? For example, I read a little bit about how some non-Newtonian fluids will increase or decrease in viscosity over time or due to particular kinds of stress.
Yeah, there's a lot of non-Newtonian fluids. They have sort of this slightly unusual behavior. The easiest example of this is silly putty. If you put silly putty, it's this sort of like putty-ish thing, right? And if you throw it to the ground, it'll bounce. So when it behaves on short time scales, it behaves like a solid, like a rubber ball. But if you attach it to a wall, then it'll flow down that wall like a fluid would, like some really viscous fluid.
Right.
So depending on whether it's a fast time scale or a slow time scale, you'll have different features. And that's sort of typical of non-Newtonian fluids.
And this is like the typical kind of cornstarch and water mix that you can make in science class.
Yeah, that stuff too. I've always wanted to run across one of those things. I've seen the videos, but somehow I just don't have a tub of cornstarch water lying around.
I think probably not many people have a tub of that lying around.
I'd like to meet them, though, those that do.
You're listening to Skeptically Speaking with Rachelle Saunders, guest hosting today for Desiree Schell. Today we're digging into the mathematics of fluid dynamics with Malcolm Roberts, PhD in Applied Mathematics from the University of Alberta. Now, during my research for the show, I also came across something called the Reynolds number, which seemed pretty important when it comes to fluid mechanics. Can you explain what that is and why it's so important to your area of research?
Low Reynolds number flows are basically laminar flows, so they're non-turbulent. And when the Reynolds number increases in your system, it becomes more and more turbulent. Basically, the Reynolds number is the ratio of your typical velocity times your typical size, your typical length scale, divided by the viscosity. This is really neat because when you put this into the equation, you can get the same behavior for a really, really large system or a really, really small system, as long as this ratio between the velocity times length to the viscosity is about the same. So you can see this when sort of when you see satellite photos of tornadoes and stuff like that, you sort of see that same shape even when you're like mixing things in a pot. And this is the scale invariance. So this is a really cool thing. It allows us to deal with one equation. We say, okay, we're dealing with a Navier-Stokes equation at a certain Reynolds number, and then we can apply it to a really big system with that Reynolds number or a really small system with that Reynolds number.
So does the Reynolds number tend to get bigger if you are using something that's really sort of thick, like silly putty or something like that? I'm assuming there's not a lot of turbulence in silly putty, whereas in something like air, there's a lot more turbulence.
Yeah, so with silly putty, you'd have the viscosity be really high. So it's on the bottom, it's in the denominator of that fraction. So that makes the Reynolds number really small if you have a high viscosity like in silly putty.
Right.
Or like honey or something like that, right? So if you have a really thin fluid, which has a low viscosity, then it will have a larger Reynolds number if you have the same viscosity and length scales. And then it'll be more turbulent.
Okay, so this is what basically causes my plane to bounce up and down through turbulent air.
Yeah, so you have big length scales of like 6,000 kilometers, like the radius of the Earth, and you have high speeds of like 800 kilometers an hour, and you have this tiny viscosity, which creates this like very large Reynolds number, which gives you a lot of turbulence.
So just so we're all on the same page here, because I know sometimes in mathematics, words mean something subtly or really different than they would mean sort of colloquially. So when we talk about turbulence, what are we talking about?
That's always actually a tough question because, everyone knows what turbulence looks like. The phrase came from Leonardo da Vinci, and it was originally used to describe the chaotic motion of a crowd. And it's been in antiquity, like the ancient Greeks had some observations of turbulence, but there's been no real definition. And it's really fun to go to conferences and like some people deal with 2D. I've dealt, myself included, have dealt with 2D turbulence a lot. And some people say that, oh, that's not really turbulence. I'm like, well, some people say it is and some people say it isn't. But the basic idea of turbulence is that you have motion on all scales, right? So you don't just have like big waves and small waves. You've got big waves, you've got middle-sized wave, you've got small waves all the way down the line. And it's unpredictable, like it's sort of a chaotic motion, and viscosity is important. So this is really the best way I can describe turbulence.
Now, I've heard the Reynolds number is helpful when it comes to testing big things like airplane wings in smaller scales. And this actually makes sense when you're talking about how you can use the same Reynolds number because things will behave the same way in different scales. So does a lot of this kind of scale testing happen?
Oh, yeah, definitely. You can go the other direction, too. There have been some experiments of dealing with like how dragonflies fly in just a really viscous fluid. Then you have this like meter-sized dragonfly wing, and then you can flap it like really slowly in this like viscous fluid. And it'll behave the same way as the smaller dragonfly moving more quickly in a less viscous fluid.
Okay, and that way you can see a little bit more about what's happening.
Yeah, and everything's much slower, so you can see what's happening much more easily.
That is very cool. Now, a lot of what you do is create simulations of these fluid dynamic systems. And when I think of simulations of this sort, I think of a lot of very hands-on physical testing that includes things like big wind tunnels and colored dyes and flowing water. What kinds of math goes into creating these simulations, and what kinds of simulations do you work on?
The simulations that you've described are sort of more like physical experiments. So when you try in an industrial process, say, you would want to first maybe instead of having to go through all the trouble of creating a wind tunnel experiment, you might want to just do a simulation on a computer because that's a lot cheaper and easier, and you can change things really easily and quickly. So that's the area that I work on. And then once you have an idea there, then you want to build it in and model in a wind tunnel to validate your simulations. And then you build a full-scale model, and then you hope everything works in between. Usually it doesn't, or a lot of the time at least, because there's so many, it's hard to get like the right Reynolds number. There's just a lot of detail going on, and you have to keep track of all this detail. And that's really, really computationally difficult.
We had talked a little bit before about how this stuff is so complex, so it would seem like a huge challenge to try and model all of those possible complexities in a computer simulation.
I found this really great blog. I think it's called fluiddynamics.tumblr.com. And they had a really interesting video, which I think illustrates this problem perfectly. And they had a video of an airplane, like a 747 or some such thing, flying over a city. And then they said, we'd like to model this to understand how it behaves. And then they zoomed in on the wing, and then there was this like little tiny stripe on the wing. And you're like, why is this little tiny stripe on the wing? And it was an area 10 centimeters across, 10 centimeters high, and 50 centimeters long. And that small area on the wing took 50,000 CPUs to compute. So
Whoa.
Yeah, right? So in terms of actual, I mean, there are systems out there with like 100,000 CPUs, which I'm hoping to be working on with this magnetohydrodynamic research. But, I mean, that still doesn't give you the entire plane at all the resolution. So what we often end up doing is just using these subgrid models. So we have a certain resolution, and there's so much data missing that we just sort of model it. And the problem is that, I mean, sometimes these subgrid models work really well, but they're a model, right? They're not a simulation. So sometimes they might not be right because the model was developed in this certain regime. And if we're not in that regime, then the model isn't telling us about the thing that we're actually looking at.
So I actually have a listener question from email that seems perfect to ask right now. And this question comes from Lane.
What did people studying fluid dynamics do before we had computers powerful enough to make models of the motion?
Well, there was a lot you could do, and there's a lot of analytic work that you can deal with understanding this stuff as well. Kolmogorov, who was a Russian researcher in the 1940s, was actually, he was really important in this. He talked about the energy spectrum of this, right? What I work on in particular, and a lot of what people think about when they research fluid dynamics, is how much energy is at what size of wave, right? So when you are looking at your MP3 player, it's got like a spectrum, right? And if it's got just one note really loud, it'll have a high amplitude at that frequency. So you can sort of see what the spectrum is like. That's a power spectrum. And Kolmogorov gave a really great prediction of how much energy is at what size of wave in turbulence. And he's got this famous 5/3 law, which tells you that you have lots of energy at large scales and it goes slowly down as you go to smaller and smaller scales. So that's one example of non-computational things that you would deal with in fluids. There's other interesting stuff with things like superfluids, like liquefied helium. You can deal with some really neat stuff because you have these vortices happening there, but they're quantized because it's quantum mechanics. So they're sort of like discrete entities, like ones and zeros, instead of continuous fractions in between and such like that.
And actually that leads into another listener question that we just got from the chat from Jim Carver.
Do we have to go to the level of quantum mechanics to understand superfluidity?
Superfluidity is entirely a quantum mechanical thing. So, I mean, I don't know a huge amount about it, but you have these modified evolution equations which take into account some of the quantum nature of the fluid when it's like liquid helium. But and then there's all these nice results about like, oh yeah, then we get these quantized vortices happening and they interact in such and such a fashion, and maybe we can understand it in terms of the vortices. But it's not an area I've looked at too much. So,
can you speak to how superfluids are different from sort of the standard fluids that we might think about?
Well, superfluids are really neat. You basically, the only one I know of, I guess, is liquid helium. When you cool it down to a certain point, which is around like 2.5, 3 Kelvin, it stops having friction inside, which is really neat. If you have a cup of it, it will, and you're suspending it somehow, the liquid helium, the superfluid part, will climb the sides because it's just got no viscosity, and it's still got surface tension. So it'll just climb the sides and go everywhere, and this lack of friction is sort of the same effect that you get in superconductors, where they have a lack of electrical friction there, so they can just conduct stuff without it losing any energy. Whereas in this liquid helium, in the superfluid, it will move stuff without losing any energy.
You're listening to Skeptically Speaking with guest host Rachelle Saunders, standing in for regular host Desiree Schell, who will return to the radio in a couple of weeks. Today I've got applied mathematician Malcolm Roberts on the line, and we're talking about how math can help us understand, and in some cases even predict, fluid and turbulent behaviors. And we'll be right back after this.
On the next episode of Skeptically Speaking, guest host Rachelle Saunders is back for part 2 of our 2-part series on the fun and fascinating world of math. Rachelle spends the whole hour with Ian Stewart, mathematician, professor of mathematics at the University of Warwick, and author of over 24 books on topics from chaos theory to symmetry and the history of math itself. That's next week on Skeptically Speaking, on your local radio station, or online at skepticallyspeaking.com.
Welcome back to Skeptically Speaking. I'm Rachelle Saunders, standing in as your host in place of Desiree Schell. I'm here today with Malcolm Roberts, PhD in mathematics from the University of Alberta, and we're discussing the math and mathematical modeling underpinnings of our understanding of fluid mechanics. Now, you mentioned before that you're working on a way of mathematically understanding fluid by basically considering it to be a wave. How does that work?
The technical word for this is to look at its Fourier series, right? Let's look at it this way first. So, my brother's a bass player. So he creates a lot of tone. And the way he does this is that he takes his taut string on his bass and he pulls it up and then he releases it. And that forms a triangular shape, right?
Right.
So that triangular shape, you could view it either as a triangular shape, which is a perfectly reasonable thing to do since it is a triangular shape. But you could also look at it in another way. And this is one of the great things of mathematics. It's just like changes of perspectives, which really show you what's happening. This taut string likes wiggling like a wave. So this triangle, you can sort of say, yeah, I guess that's sort of like this smooth wave, which just sort of humps up a little bit, right? And you say, well, it's sort of halfway up one side of the triangle, it overshoots, and maybe at the peak of the triangle, it undershoots. But it's, it gets the idea across that at least the string has gone up.
Mm-hmm.
That would be the first Fourier mode, the first wave that you want to use to describe the shape of this string. So then you add more on. You have like a wave with a higher frequency. And so where the first wave overshoot, we have it go underneath a bit. And then where it undershot, we have it go up a little bit by adding another wave on. Mm-hmm. And we keep doing this. And we add more and more waves together. This is basically, instead of describing it as a triangle, which is a shape where we have the deviation of the string, how much it's moved from its rest position, and we say, okay, well, when we're this far along the length of the base, it's gone this far, and when we're a bit farther, it's gone this far, and it ends up looking like a triangle. We can look at it that way, or we can say that this is a superposition of waves. This is this sort of a spectral method of simulating how fluid moves. We look at the waves, we see how the waves interact, then we put that together to get the picture of how it actually looks physically.
So what are the advantages of doing the mathematics this way?
Like I said, it's to change the perspective. So you've got a couple of things happening. When you have a fluid, the acceleration of the fluid is, well, there's a viscous term, right? So there's this friction term due to viscosity. And when you look at this in terms of waves, that viscous term looks really simple because the friction for a certain wave is just proportional to its frequency. Mm-hmm. So where you had this big complicated thing before, now you have a really simple term that you can look at. So another important term, well, there's the pressure term, and we deal with this in a certain fashion. The other term is the advection term, right? So when fluid is moving, it tends to drag fluid along next to it in the same direction. And this is the hardest term to deal with computationally because the friction term is a linear term, and linear is pretty simple to deal with. We have lots of good theory about that. But the advection term is a quadratic term. So instead of just being linear, it's like something times something, and then it gets really complicated. So, and when we deal with that, in Fourier space, when we transform this and look at it in terms of waves, this simple multiplication becomes a convolution. And much to my surprise, I actually spent like a year and a half researching and putting papers out about how to calculate this efficiently.
Okay. Does this have anything to do with the fast Fourier transform?
Indeed. It does have everything to do with the fast Fourier transform. The method that we use is called the pseudospectral method. So we deal with everything, like if you would deal with just a sort of straightforward spectral method, this convolution, if you have a domain of size like, n points, so that's the resolution you're looking at, that's what fits into your computer. Calculating the convolution involves n squared operations. So when n is like 10,000, that's really quite terrible.
That's a lot of computations.
Yeah, and it's got terrible numerical accuracies, so you'll end up with waiting a long time for a not very good answer.
Which is not ideal.
No, which is not what we're wanting out of these simulations. Sometimes in mathematics we like just looking at random things, but sometimes we actually need to know things. There are people asking us. The pseudospectral method is like we do everything in spectral space. We just look at it in terms of waves, except this one convolution. So we could use a Fourier transform, which involves n-squared operations, and then deal with this convolution back like in physical X space, like it's a multiplication. But the problem is that, the Fourier transform involves n-squared operations as well, so we haven't really won. But the fast Fourier transform involves n log n operations. So when you're looking at that, if your domain size, choose an easier number, is like 1024, then n squared is 1024 times 1024, but n log n is 10 times 1024. So you're 100 times faster.
Okay, so it's actually just a really fast way of crunching a lot of numbers.
Yeah, and it's got an interesting history as well. It was actually first discovered by Gauss, and I was caught once for mentioning this and not having read the original paper because I was in Latin. But, I'm
That's
like,
a good
yes,
reason.
okay. Well, I think there's online Latin translators, so eventually I'll get around to that. But it was rediscovered, the fast Fourier transform was rediscovered a lot of times, and it's really become really important in terms of signal processing and digital signal processing and all this type of stuff. The fast Fourier transform basically breaks things down into waves or sines and cosines. And for example, the Ogg Vorbis audio format is a modified cosine transform. So that's one example of where maybe some people have used FFTs without
really knowing it.
Yeah.
I also wanted to talk a little bit about the Navier-Stokes equations.
Yes, these ones.
Yes, what are these equations and why are they so important to your field?
Well, the Navier-Stokes equations seem to do a really good job at how fluids move. They've got the acceleration proportional to, well, you've got some pressure pushing things along, you've got the advection term, and you've got the friction due to viscosity term. And that's all it is. And you also maybe have some equation of state saying, like, what happens if I squeeze a bunch of air together? Does it just squish out the sides, or does it get, like, slightly denser? Okay? So this is all you have. There's currently, and this was issued as one of the Millennium Problems by the Clay Mathematics Institute, if you can figure out whether there's a smooth solution to this, then there's $1 million in it for you.
So my understanding is that these equations they're pretty good at predicting things most of the time, but once we start getting in extreme situations or at really small scales, they actually don't work very well. Is that correct?
Yeah, well, if you get to really small scales or really like dispersed gases, like if you have an outer space, it's more particles. So you wouldn't use the Navier-Stokes equations there. The Navier-Stokes are a continuum approximation of reality, right?
Right.
So we all know that the air around us is made out of molecules, right?
Right.
So, but we don't deal with those molecules individually. There's so many of them, and there's such a concentration of them in a certain given bit of space that we can deal with that like it's a continuum. And that's a totally useful thing to do, and it's totally valid, and it makes really good predictions. But of course, when you come down to it, it's all a bunch of individual molecules zipping around.
So when we're talking about smoothness in this context, what are we actually talking about?
Well, I'm just talking about like discrete versus continuous. If you look at sand closely, like if you just got a few grains of sand in your hand and you're really interested in exactly how these grains of sand move, then you would want to model them discretely, right? So you look at each individual grain of sand and you look how it moves individually. Maybe they bounce off each other, stuff like that.
Right.
But if you've got such a large number of them that it sort of moves as a mass of sand as opposed to individual grains of sand, then you use a continuum approximation to that, right? So you say that they're so close together and they move like it's a fluid that I'm going to apply the continuum approximation, and I'll get really good results from that because this does really look like a continuum. And the continuum approximation is a really valid and useful thing to do. There's some cases where it doesn't work, where you really need to look at things discretely.
This is Skeptically Speaking, hosted today by Rachelle Saunders. We're talking fluids, turbulence, and math with Malcolm Roberts from the University of Alberta Mathematics Department. So this summer, you're heading to France to work on magnetohydrodynamic turbulence simulations. What exactly is that?
This is basically, you take fluid dynamics, but instead of dealing with something like water or air, you deal with charged particles moving. Typically, one example of this would be the aurora borealis. So you've got some air moving up there, but you also have electric particles like electrons and other ions kicking around. So you have the magnetic field, and you've got the electric field, and then you've also got the velocity field. So you have to combine all of these things together into one thing which moves as a mass.
So what are the applications of this research?
Well, I think the most interesting application is the sun or other stars. The sun is made of plasma, so it's a gas, but it's become so hot that the electrons and the nuclei have split off a little bit. So you have charged particles moving. And so you have these charged particles moving, and then they interact together to get these gigantic solar flares which follow electrical field lines, but the electrical field lines are influenced by how the fluid moves. So it's a really complicated system and really beautiful looking. You've seen all of these solar flare pictures, and really important to know about too.
When I was researching this topic, magnetohydrodynamics, I was actually really excited to find out that this has some geophysics applications right here on Earth, including our understanding of the Earth's magnetic field and how it flips every few thousand years, which I found really fascinating.
Yeah, well, it's going to have some interaction because the core of the Earth is also a molten substance, so it's a fluid. It's a really viscous fluid, and it moves slowly. But it's also going to have, because it's rotating and it's an electric, it has some magnetic core. So it's going to have this fluid aspect. It's going to have a magnetic aspect. And that's going to interact with the solar winds, which is this magnetic and electrical field whizzing by. So, yeah, really interesting stuff happening there, too.
I have a question from email. This question's from Corinne.
Can you explain why the phrase applied mathematics isn't a contradiction?
Well, applied mathematics is you just take mathematics to solve problems. And you use problems to learn more about mathematics. In some ways, the pure and applied mathematics division is sort of an anachronism because, like the string theory stuff, which is, there's really interesting mathematics, but it's trying to solve a physical problem. Mm-hmm. But it's of a area which would be typically viewed as pure mathematics in the past, except they found this one application with string theory. Even things like number theory, people used to be proud that their mathematics that they dealt with, this number theory, had no applications at all. They were just doing mathematics for mathematics' sake. But now we have all this cryptography stuff, which is completely number theory. Like if you find a good way to factor numbers, you can break crypto systems. But mathematics is about the universe. I often wonder if there was another universe, would mathematics, if we could travel to some alternate universe, would mathematics be the same? Is it a property of the universe, or is it something we've discovered, or is it just a way that we understand the world around us? Right. I don't really know.
Right. So it's sort of the idea of, is it just the way we're interpreting our world, or is it actually something intrinsic within the world?
Possibly, but there's a lot of math out there, which is really crazy. And it seems to pop up. If we could design mathematics in any way that we wanted to, we probably would have designed something simpler and easier to deal with, so that we could just use it and then understand the world much more easily, in a purely practical sense. But it doesn't seem to be like that. So
does a lot of math tend to start out in the sort of pure mathematics sphere, kind of like you said, math for its own sake, and then transition to applied mathematics as we find use for it?
Sometimes, yeah. Some mathematics we still haven't found use for, and no one knows if we ever will. But I think, I've read some history of mathematics books, which seem to, the author was at least of this similar opinion. Mathematics seems to be discovered. It's like we started in Babylonia trying to figure out where people's land was after the floods, because we'd have to figure out, we couldn't put stakes in the ground, so we had to do some geometric thing to figure stuff out, to figure out where stuff was, where this farmer's field ends and where the next begins. And they started dealing with that, and then they we're trying to write everything down, and then they noticed that the diagonal of a square wasn't quite as easy to write down as they thought it might be, because that's square root 2, mm-hmm. which is actually a pretty cool, weird number. So it keeps popping up. And I've had arguments and discussions with various friends about whether, this is all based in reality or just something we made up. And, we haven't solved this yet.
So I have another email question from Dr. Light.
I've been out of school for over 30 years. I'm trying to keep up with science as best I can. Can you recommend a good idiot's text to refresh my math skills to a level that would be good enough to cope with modern physics or chemistry concepts?
The usual go-to text is Wikipedia for lots and lots of levels. They've done a really good job of having an introduction which is very understandable. And then you go on a little bit farther and there's some, stuff that would take a little while to understand. Then you go a little bit farther in the article, and it's like really deeply complex stuff. So that is always a good way to go. There's a variety of really excellent open source math books available. So those are good. And the Khan Academy has been doing some really cool stuff as well. And they've recently hired somebody else. I forget her name, but she does the snakes thing, which I think is really cool, and sort of has that joy of mathematics, which I think is really instructive as well. I haven't really dealt with it too much myself, but I think those are some really cool resources, which I think people could check out if they wanted to.
And so obviously something about math. When I was in high school, I have to admit, math was the very last class I ever wanted to go to. And now as an adult, as I read more science books and learn kind of some of the really cool stuff that math is used for, that it's not all just like writing and solving equations, I'm getting more interested in it. So what was it about math that kind of lured you in?
I guess part of it was I was fairly good at mathematics, so I wasn't dissuaded from it. And I had some really interesting math teachers in high school as well. I remember Miss Nicholas. She was one of the first 2 women to get a master's degree in mathematics out of the University of Toronto, which is pretty cool. And after a while, come 4th year university, I realized that when she was telling me that she had her chalkboard and she was drawing 2-dimensional Euclidean grid, right? And then she was asking us where infinity was, and she said, like, oh, it's over in the next room. And really what she was talking about was projective geometry, which I'm not going to totally describe, but it's really cool and a nice way to think of things. And that sort of, I think, got me interested in a little bit, because I found someone who was passionate about mathematics and really knew their stuff who taught me. So that was cool. I also started in physics, and I was really interested. I started my bachelor's degree in physics before I moved over to applied mathematics, because I found that I liked it more, and coincidentally I was doing better in it. So that always
a plus.
helps. Yeah. And I don't know, it's really fun stuff. It's little games that we can come up with and little puzzles, and whenever you solve a puzzle, you usually find a deeper puzzle underlies it, and then you sort of are still confused, but you're confused about more important things on a deeper level. So, I don't know, it's just really fun. And we've been trying to visit schools. The University of Alberta Graduate Association, the Mathstat Graduate Association, has an outreach program. And also, I have a colleague who did a master's in mathematics in a very abstract area, really not applied math. And she's over at the Space Science Center, which might be the TELUS World of Science right now, I'm not sure. And she's been doing these math camps, which is her initiative, and those have been really successful. So I think one way that I got involved in mathematics was being inspired by teachers who knew a lot about it and were passionate about it. And we're trying to do that a little bit more for other people, because, as you said, understanding some of the really cool science happening right now really relies on mathematics a lot more than it used to.
That's really fantastic. Before I let you go, I just have to ask you as the expert, how do you pour the perfect beer?
Well,
very important.
Very important. This is not the perfect beer, but you'll see where this will come in use, I think, by the end of it. So, turbulence sends energy from large scales to small scales. And small scales in your beer, if you have a lot of energy at the small scales, you're going to have pressure differences. And these pressure differences are going to cause bubbles to foam. You're going to get, so when you just hold your beer bottle like a meter up above your glass and pour it down, there's a lot of head, as you would well imagine. That is a bad pour. So, if you're trying to minimize the head, which is not always perfect, but sometimes, is what you want to do, for example, with champagne, then you want to pour it down the side of the glass, which minimizes the energy injection rate, because you're not, you're pouring it slowly. Mm-hmm. And then this energy injection rate minimizes the amount of turbulence that you have. And the less turbulence, the less energy at small scales. But, and this is a theory that I've been wanting to check, there's this other, energy is an important conserved quantity here, but in 3 dimensions, there's this helicity thing. And that's the tendency of the fluid to move like it's following a corkscrew, right, like in a helix fashion. And instead of, when you pour your beer into your glass, instead of having it go straight into the glass, if you angle it, so it sort of corkscrews down the side, then it seems to, and this is really interesting, minimize the amount of turbulence, and the less turbulence, the less bubbles that are formed. And then you just sort of keep the bubbles in the champagne a little bit more.
That is very, very cool.
So, and I'm also looking for grants to, research this more.
I think that is an excellent use of our public funds.
Excellent.
Malcolm, I am sad to say we are all out of time, but thank you so much for being here today.
And thanks very much for having me. It was a pleasure talking to you.
If you want to learn more about Malcolm Roberts, fluid dynamics, or applied mathematics, there will be links posted to Malcolm's website and the blog we mentioned earlier. And while you're on our website, we would love for you to click on the links to our Facebook page, our Google Plus feed, or our Twitter feed, all of which are most excellent ways to keep in touch. You can also visit Skeptically Speaking on iTunes, where you can download past episodes, subscribe to future shows, or leave a review. Thanks for listening to Skeptically Speaking.
Bring it on, the skeptics await your letter. Your call, tweet, homing, pigeon, whatever. Desiree Schell gonna raise a little hell, metaphorically that is. 'Cause we're skeptically speaking.